Okay, let's continue. The last speaker of this morning's session is Pinyan from Microsoft Research in Beijing. He will talk about approximate counting.
Thanks, organizer, for inviting me here. I'm Pinyan from Microsoft Research, and today I will talk about kind of a summarize of a recent approach of designing approximating counting algorithm via the correlation decay technique. This kind of follows the previous talk by Jingyi also about counting problem, but in some sense it kind of further away from the theme of the workshop. But I'm sorry for that. I hope you still find it interesting somehow. Okay, here is the okay.
Hello, good to see you.
Sorry for that. Here's the plan of this talk. First, I will introduce counting problem, as Jing already did that in the previous talk, so I have an easy job here. But will introduce a new perspective of counting problem, which relates a probability distribution over instance of a counting problem. Then I will demonstrate our main approach of this new design technique, whereas the most simplest kind of constraint system, which is a two-state spin system. Basically, this is a local constraint system where each constraint is a binary constraint. It only involves two variables, and each variable takes value from a Boolean domain. So it's a kind of very simple case. Then I will briefly mention some more results and extensions for the much more complex systems like the multi-spin system and the multi-party system. Okay, so counting problem, as already said by Jingyi. So that set is one of the most canonical example of a computational problem, which, given a CN formula, ask is there a system assignment or not. This is a decision problem, and the counting version actually count how many satisfying assignment of a CN formula. So similarly, we can count many other properties like the coloring of the graph, like independent set of graph, like counting the perfect matching of a vector graph, which is a permit of the adjacent matrix, so on and so forth. So these are all very natural and interesting computational problems. But some of you may still ask, why do we care about the number of solutions for a constraint satisfaction problem? So here, I would like to list more problems which may not look like a counting problem at first, but there indeed is. The first example is the probability. Probability is actually indeed a counting problem, which counts the number of samples in a sample space where a random event happens. So this is basically a counting problem. If you have a better algorithm to do that, you can make a better decision and even win money. And the second example is the partition function in statistical physics, which is indeed a weighted counting. And statistical physics, partition function is a very important quantity for describe the physics system, and which encode many other information like the entropy, energy of the system, and so on and so forth. Third example is that, like in machine learning field, there's a model called graphic model, and there's one important task of graphic model is inference. Basically, compute the marginal probability of some variables and maybe condition on some observations. And these are actually counting problems. And many other problems like the queries on a probabilistic database or some optimization problem for a stochastic model, so on and so forth. So as already said by Jing in the previous talk, there are many dichotomy has to be proved for the exactly counting framework. And actually, from the dichotomy, you will see that for most of the case, the problem is sharply hard. As I said, for the tractable case, it's not full rank. It's kind of a major zero thing. So most of the problem is actually sharply hard. So we would like to further classify the sharp hardness problem in terms of the approximation. So we want to show that certain problem is approximable and some other problem is still hard even you allow approximation. So let's define more precisely what do we mean by approximate counting. So let epsilon be an approximation parameter and z be the correct counting number of an instance. So the algorithm needs to return a number which is called z prime, which is within a relative L epsilon from the correct value and in time poly of n and 1 of epsilon. So this is called FPTAS, fully polynomial time approximation scheme for the problem. And another a randomized generalization for that is called FP-RAS. Okay, any question with that? So to the end of this approximate counting, I would like to introduce a new perspective of counting problem, which relates probabilistic distribution of a counting problem. So let's use one concrete example, like the independent set problem or graph. So here let's denote ISG be the set of all the independent sets of graph G. And so the counting problem actually asks the size of this set. Okay, so here we introduce a kind of a distribution. Let's say X is choosing from this ISG uniform at random. Basically, X is we can pick a independent set of graph uniform at random. Then, from that, actually, we can define the probability that some vertex V is in a choosing independent set or not. Okay. So here I use not for the notational simplicity of some following, but it's the same thing. Okay. So for this case of independent set, we all know that the empty set is an independent set because it contains no vertex, so it's independent. And so what's the probability that this randomly choosing X is happen to be the empty set? From one hand, it should be 1 over the size of the independent set because each independent set from this set is choosing randomly, uniformly. So this is 1 over the size of the independent set. Then we can also write this term from other perspective. So this means that all the vertices are not chosen in the independent set. So this can be written down as a conditional marginal probability. Right? This means that it's equal to the probability that the first vertex is not choosing, and given that the first vertex is not choosing, and the second vertex is still not choosing, so on and so forth. This is a chain of conditional probability, and this property X is equal to empty set is equal to this product. Right? Here, this GI is just a modified graph by deleting the previous vertex because they are already. This basically indicated that's the condition that all the previous vertices are not choosing in the independent set. Okay. So put these two equations together, we get that 1 over the size of the independent set is equal to the product of this probability, marginal probability. So given that, if you can compute these marginal probabilities in the left-hand side or approximately compute, like estimate these probabilities, then we can actually compute or approximately compute the size of the independent set. Okay? So then the main task is actually to compute this marginal probability. And there are two ways. The traditional way is actually to estimate this marginal probability by sampling. This is a very beautiful line of research which actually relates this counting with sampling, and it actually gives a FP randomized algorithm to approximate counting because this value is estimated by sampling, random sampling. And here actually I would like to talk about a new approach, which actually we don't do any random sampling. Actually, we approximately compute this marginal probability directly and deterministically, and which will give FP-TAS for the counting problem. Okay. So to make it more formal, I will give introduce the formal definition of the spin system, and here's the spin system, and this is actually almost exactly the same as the graph homomorphism defined by Jing in the previous talk. And here, one more thing is that we have the is called the external field, which is called vertex function. I will define this. Okay, so this spin system is a term from the statistics physics. It's describing of some particle system, and the vertex are the particles of the system, and the edge describes the neighborhood relation of the particles. And here the spin state is a finite number q. Q could be equal to 2 or 3 or so on. It's a finite. Actually, the spin state is up or down, something like that. So it's all the configuration, possible configuration of a spin. Then a configuration is basically is a description of all the spin states for all the particles in the system, which is basically a mapping from the vertex to the spin states. Okay. There are two functions which describe the spin system, which is one is the edge function, which kind of describes the kind of the local interaction of two particles, and which will gives which takes the input of the two combination of the particle, the state spin states of the two neighborhood particle, and which gives a real value, non-negative real value, which somehow indicates the energy of this local interaction. Another function is a vertex function, which actually mappings the spin states of a vertex to a non-negative real number, which actually states that if this vertex is isolated, what is the preference of the spin states for that particle. So given a configuration, the weight of this particular configuration takes the product over all the contribution from each edge and each vertex. Evaluate on this particular spin state. Okay, then the partition function is basically the sum of all these weights over all the possible configurations. Okay, these are the same definition in the previous talk. So for that, this basically is a weighted counting problem. It's a sum of product expressed. Then, so the probability distribution over this field is that we actually this weight of a configuration gives rise to a probability distribution. Basically says that the probability of the system being in a particular configuration is proportional to the weight of this particular configuration. Here, this partition function actually acts as a normalized fact because this is a summation of all the possible weights. Okay, so this definition, which is also called the Gibbs measure or Gibbs or the Boltzmann distribution in statistics physics, and this actually gives joint distribution of all the possible particle in the system, and from this joint distribution, we actually can define the marginal distribution of the state on a particular particle or vertex V. So this define if we sum over all the other possible particles, then we can get a marginal probability for a particular vertex to be in one of the particular spin states. And we can also define the conditional marginal probability if some of the vertices have a fixed configuration. So some of the vertices in the system may be fixed for some reason, then we can talk about the marginal probability, the conditional marginal probability of other vertices. So all the definition here looks good. Okay, so I said this spin system is a model in statistics physics and also in applied probabilities. This can also be viewed as a framework of many combinatorial counting problems. I will get that later. And it has many applications in machine learning, coding theory, and so on. And why this can be viewed as a counting problem? These two examples are already shown by Jing in the previous talk. So if this edge function is like this matrix, the 3 by 3 matrix, is 0 in the diagonal and it's 1 in the off-diagonal entry, then the partition function of this spin system is exactly the number of 3 coloring of a graph. Because this 0 means that for the 2 adjacent vertices, they are not allowed to have the same color. And similarly, this bit matrix also read here previously, it can be interpreted as an independent set of the graph. So, and the partition function exactly counts the number of solutions. This is a problem. Okay. So for this kind of spin system, there are many tasks should be done, and one is to compute this marginal probability, which is very important in the machine learning community. They want to do this influence on this graphic model, and we may sometimes we would like to sample a configuration, global configuration, with respect to this Gibbs measure. Okay, and other task is I already mentioned as our central task, which is compute the partition function. And it turns out that all of them are actually kind of related. If you can do one of them efficiently, you can do other also efficiently, in terms of approximate counting. Okay, actually in the applied field, actually they have a very famous algorithm to compute all these tasks, and which is called the brief propagation algorithm, which is also called the message passing algorithm. This is kind of a heuristic method, which is widely used in statistical physics, machine learning, and many other applications. And the algorithm behaves very well in certain applications, but the problem is that there's no much theoretical justification for that, unless the graph is very special, like in a tree. If the graph is a tree, then there's a theory saying that this brief propagation will compute the right number. So here's a very rough, high-level description of what the brief propagation algorithm is. It actually starts with some very kind of arbitrary initial guess of the states of each particle. Then the algorithm recursively refines the guess based on some local information. Basically, you refine your guess of the states or the probability of certain particle based on the neighborhood of this particle. And you do that over again, and after a finite number of fixed number of iterations, you actually just output the current state after the recursion. The main problem with this heuristic algorithm is that you don't know if this process will actually converge to a number. Even if it converges, we don't know if it converges to a correct number or not. So that's the main question. And for these three steps, actually the first step is more problematical in some sense because this guess is quite arbitrary. And on the other hand, you cannot have a really good guess. If you already have a good guess, you don't really need to do the recursion anyway. So in order to prove kind of convergence and correctness, the idea is that you want to say that the final output is almost irrelevant to the initial guess as long as you perform the recursion for long enough steps. That's the idea. Okay, so the initial guess will not affect the final output too much as long as you already do that again and again for long enough steps. So this idea is actually captured by this notion of correlation decay, which is one of the keywords in my title. So let's define this correlation decay for the spin system first. So a spin system of a family of graphs said to have an exponential correlation decay if that's the marginal probability of a certain vertex of the particle conditional on configuration of another subset lambda is very close to each other if this lambda is kind of far away from your vertex, which basically says that the configuration which is far for the vertex which is far away from you is have very small influence of your marginal probability. That's the main idea. Okay, so here I call it weak correlation decay because there's another different notion called stronger notion. Where actually here we say that this lambda is a subset of vertex which has fixed configuration, and we want this vertex to be further away from this set. But the two partial configuration could be have the same states for certain vertex and for different states for other vertex. And if they have they have a same spin states, then it should be intuitively it should be okay because in the two partial configurations they have the same states even if it's close to you because it's the same in the two conditions. That's not affect much. So in the strong correlation decay, this distance is defined from this vertex V to only to the subset of lambda, where the partial configuration are not the same. Okay.
Distance is distance in the graph.
Yeah, distance in the graph. Yeah. Okay, so this is one definition in the spin system, and as I said, this is also very related to the Cliff propagation, and there are many different ways to interpret this property of collision decay. One way saying that is that this describes the significance of long-distance interaction. If it's of collision decay, there's kind of the long-distance interaction is relatively insignificant. Also, if you view the subset lambda as kind of the boundary of the system, this is talking about the effect of a boundary system, boundary conditions where how they will affect for the vertex which is far from the boundary. And this is not so direct, but it's very related to that. This is also talking about the effect of the initial guess in the propagation. Because in the propagation, you actually recursively refine your guess based on your local information. So after like L steps, only the information which is within the distance of L can have effect on you after this recursive recursion, and the information on the vertex which is further away cannot affect you. So only if the system have this kind of collision decay, there's a hope that the pre-propagation algorithm can work fine. And for statistics physics, the big question here is that how to characterize the systems with this property of collision decay, because a system with collision decay and without collision decay will behave very differently, both in terms of the physical property or the computational property. Okay, actually, our main result for this part is a characterization of this property for one family of spin system, which is a two-state spin system, which is a special family of spin system where only have two states, so Q is equal to 2. For that, there are only a 2x2 matrix and a 1x2. And for that, we can do some normalization because a global fact will not affect will not affect the relative weight and will not affect the distribution at all. So we can normalize that off diagonal as 1, then there's a 2 parameter for the H function, and then the 1 parameter for the vertex function. Okay. So basically, a two-state spin system can be described as 3 parameters, beta, gamma, and lambda. And there's two families of this two-state spin system. It depends on this beta times gamma is larger than 1 or less than 1. And I would like to mention that if beta times lambda is gamma is equal to 1, then in some sense this system is degenerate, because this can be decomposed into 2 rank 1 vector, and in that case there's no interaction among the two edges of the two neighborhood particle, and in that case the physics system is trivial and the computation problem is also trivial, which is one of the tractable cases in the dichotomy theory. And so when this is less than 1 or larger than 1, behaves very differently, both in terms of physics property and computation property. So in this work, we mainly focus on this anti-ferromagnetic system where this beta times gamma is less than 1. There are two special two-state spin systems which is widely studied, both in physics and in computer science. One is this hardcore model, as I mentioned. This is basically in our world, it computes the independent. It's an independent set of a graph, and this is another special case called the Ising model, where the beta is equal to gamma, and it's anti-ferromagnetic Ising, then it's less than 1. To introduce our characterization of the collision decay for this special system, actually we need one definition, which is called the uniqueness condition of the system. And I'm not going to the detailed definition of that. Basically, the message here is that if we are given the parameter beta, gamma, and lambda, actually we can numerically, at least numerically test this property efficiently, but we don't have a closed form for that.
What is the
D? Yeah, good question. D is kind of the degree of the graph. So It's the I will tell you in the film. Okay. More precisely, I should define this as something called a D uniqueness, and it's in the final localization. I will talk about this is unique up to degree something or on degree something like that.
It's an additional parameter.
Yes, I don't. Yeah, sorry. Okay, this is one message, and another message basically saying that this requirement basically saying that on the fixed point is kind of a contractive mapping, which is easy to show that this is indeed a necessary condition for the correlation decay on the system with degree D. And the localization was first approved for this special case of hardcore model by Weitz, actually showing that this uniqueness is not only a necessary condition but also a sufficient condition, in the sense that this strong correlation decay holds on all graphs with maximum degree delta if the uniqueness condition on infinite delta regular Qi holds. Here, this condition will transform to the numeric condition where this D is equal to delta minus 1, because in the recursion you will, yeah. Then this is the numeric definition of this condition, this uniqueness condition. Okay, so there's two integrally of this proof for the localization. One important construction is that is so-called self-awarding working Qi, which actually transforms a general graph to a Qi, which keeps the marginal probability of the root. I will get into that later. And another integrally used is that it's kind of the monotonicity argument, which showing that any Qi with degree at most delta decays at least as fast as the complete D-regular Qi. So basically, this technique enables us to only prove the correlation decay on a Qi rather than a regular graph, because any graph can be transformed to a Qi. And this second step showing that any Qi with degree at most delta decays at least as fast as delta regular Qi, which delta regular, so the decay on the delta regular Qi is exactly the uniqueness condition. So that's related to the condition of uniqueness for the correlation decay. So here is the definition of the self-awarding working Qi. Basically, that's starting from a vertex V, like this vertex 1, and we can expand a Qi. This expansion of the Qi basically enumerates all the possible simple paths of this graph starting from this vertex 1. So this is a 1, 2. This is a 1, 3. Yeah, this is 1, 1, 3, 4. Like 1. This 1 will be closing the closing the loop, and the final one will be already fixed in some sense. I will not go to the detail. There's a procedure to transform a graph from starting from some vertex to a Qi. Has a property that the marginal probability of this vertex in the graph is exactly equal to the marginal probability of this root of the Qi in the new graph. So given that it's enough to prove the correlation decay on Qi rather than a graph. And but the one thing is that the size of the self-awarding working Qi could be much larger, and it's actually could be of exponential size compared to the original problem. It actually enumerates all the possible simple paths. And one good thing is that this construction actually works not only for the hardcore model but for all the two-state spin systems. So we will also use that in our proof. But the bad thing is that this only works for the two-state spin system. Then later we will further extend that to multi-spin system or to multi-part system. It's no longer work. Okay, later for the special case of Ising model, it's also the same statements was also proved, which actually showing that the uniqueness condition is both sufficient and necessary for the correlation decay. Because for that, they also have the same monotonicity property. Our main effort is to try to extend this this localization for special system to general two-state spin system. Then the most difficult part is that the monotonicity condition no longer holds for the general two-state spin system. And so then we need to prove the correlation decay for the general Xu, not only the delta regular Xu, which delta is with the maximum degree. So to overcome that, actually, we finally showing this kind of localization, which says that the system is of correlation decay on all the graph with maximum degree delta, if and only if this system have this uniqueness condition for all the degree up to delta. So it's not only for the delta regular Xu they have a uniqueness condition. It's for the degree from like 1, 2, 3 up to delta. They all have this uniqueness condition. Then we can say that the system is of correlation decay. And in particular, if this uniqueness condition actually holds for all the degree, there's no constraint of maximum degree, then this system actually have the correlation decay property for all the graph. So this kind of things have not been seen for the special case like hardcore model or the Ising model, because for this kind of two special system, there's no when the degree is large enough, the system is always not decay. So this is kind of a new phenomenon for the general, for certain range of the general two-state spin system. And with this kind of localization of the correlation decay and the general and standard approach from this marginal probability to counting, and we can have a kind of algorithmic implication of our result that we obtain FPTAS as long as the system satisfying the unique condition to compute the partition function or to compute the marginal probability or to sampling. And this algorithmic result is in some sense tight because there's a matching hardness result showing that if the system does not satisfy the unique condition, then it is already NP hard to approximate the partition function of the system.
This is true just in the anti-ferromagnetic case or in general?
Anti-ferromagnetic system, yeah. Actually, for the ferromagnetic system, it's the final localization is still open. There's many non-resolved, but it's not complete yet. Okay.
But the ferromagnetic Ising model is also known how to count, right?
Sorry?
For the ferromagnetic Ising model, there is an approximate count.
Yes, there's yeah. Yeah, exactly, yeah.
That's also it.
Yeah. For the Ising model, it's easy, yeah. But for general two-state spin and ferromagnetic system, if there's no external field, then it's always easy. And if there's an external field, then recently we proved that in certain ranges it could be hard. But the hardness is not NP hardness. It's called a base hardness. Is as hard as counting the independent set for a bipart graph, which is conjectured to be hard. Okay, so here I will give a general idea, a high-level idea of how the proof goes. So here is the same identity I showed before. This basically in the previous example we're showing that the empty set is an independent set, so we can use that as a bridge point to relate the partition function to the marginal probability. Here we can choose kind of any configuration like the all zero function. This can be in one hand side as the weight of the configuration time over the partition function. On the other hand, it can be like a product of some marginal probability. So if we can kind of estimate this marginal probability, then we can approximately compute this partition function. That's the same idea. Then with the correlation decay property in hand, we actually can estimate this marginal probability by the local neighborhood. Basically, we can truncate this self-ordering working tree up to the logarithmic depth. Then from the leaf, with using dynamic programming, we can compute all the marginal probability from the leaf to the root. Then this computation will give a good approximation for the marginal probability. Yeah, here's the standard way, but in the previous result, like hardcore and Ising, that's good enough because the maximum degree of the graph is bounded. So the logarithmic depth is over polynomial size. And if for unbounded degree, then this is no longer true because if the degree is n, then this is n to the log n. So To overcome that, actually, we introduce a new, stronger notion of correlation decay, which is called computational efficient correlation decay. Basically, for that case, if this the degree of the vertex is kind of super constant, actually, we are showing that it's not only the correlation, the error not only decays by a constant factor, but actually decays with a super constant fact. And this is a formal definition, or we call this M-best depth, which actually is a refined definition of these depths. And we are showing that the exponential correlation decay also holds with respect to this new definition. And with this new definition, actually, this decay will support FPTAS for any general graph. So that's one thing. And the most difficult part, actually, how to prove the correlation decay. The proof says saying that if we already have correlation decay, we can have the algorithm. That's the easy part. So how to prove the correlation decay? The idea is that we're using the self-founding working tree to get the expansion, and then for the tree, as there's independent for or the sub-tree, then we can write a recursion from the marginal probability of the root of the sub-tree to the root of the tree. That's that definition of the local constraint. Then we want to say that we truncate this self-founding working tree at some depths. Then in the boundary of the truncation, we actually have a kind of arbitrary guess of the probability. So there's an error there, and we want showing that the error for each subtree will actually induce an error for the root of the tree, and this is the relation for the error by this partially derivative function. And so if this error of the root is bounded by this quantity, and this is the maximum of the error in the subtree. So if this quantity, this ratio, is less than 1, then we are happy, because after one step of the recursion, the error decreased by a constant factor. Then that's good enough to showing the exponential correlation decay. But the thing is that this partial derivative is a function of all the variables p, and it's usually not the case that this quantity, which is a function of many variables, is always less than 1 to all the choice of this variable. That's very, not easy thing. And so, which means that this may not be correct stepwise. So then one new idea we used is using a protection function to amortize that. The idea is actually quite simple from a mathematical point of view. You actually introduce a bijective function phi from non-negative real to non-negative real. Basically, we mapping this marginal probability p into a new domain, which is called Q. May not have any physical meaning, but just a mapping, a mathematical mapping. Then this is a bijective function mapping. So this the recursion on this p, this f function on the p, actually induce a recursion on q. Okay. For each vertex v, there's a value for some marginal probability, then which induces a quantity of q. And by this bijection and the recursion of p, we have a recursion for q. Then the idea is that you want showing that in terms of this q, the error actually decreased by a constant fraction on each step. Here, the good thing is that we have the freedom to choose this phi function. Okay, and also the difficulty is also how can we find this kind of partition function so that this after the mapping, this new quantity will be the error of this new quantity will decrease by a constant fraction on each step. And put it more mathematical, and since in this audience there are many mathematicians, so this basically saying that there are function, kind of recursive function, and we want showing that this function is contraction in the sense that the Jacobi matrix on any vector will decrease the norm by a constant fraction, and this may not be true for the function f, and we want to find a bijection mapping, and so after this mapping, this become contracted. And I don't know if there's any mathematical tool or theory which can be used to decide if there such mapping exists or not. And the effect of this mapping actually can be viewed as a local Riemann metric on the space. And basically, we're saying that there's a mapping on this space, and you want to define some local linear metric on the space such that given mapping on this space become a contracted mapping. So I don't know any mathematical tool can solve that. We have a little. Maybe I should stop here because the later I will talk about multi-spin system and multi-path system. Maybe I will list some of them. Just like for a couple of minutes. So multi-spin system means that the domain of the variable could be not 2, it's larger than 2, and the multi-path system says that each constraint may involve more than 2 variables. And the one obstacle is here that the self-ordering work tree does not work anymore. And to overcome that, actually, we introduced a more conceptual notion which is called a computational tree, which actually relates the probability of certain variable on certain instance to neighbors in a smaller instance. So this computational tree is no longer an instance of the ordinary system. On each vertex of the computational tree is the variable on a certain modified instance, and this only defines a value, which could be the marginal probability. Then this value can be computed as a recursive function for some other values. So basically, this is still a tree, but this is no longer an instance of the ordinary system. And we can similarly define correlation decay on this computation tree, which basically says that if we truncate this tree at certain depths, then the estimation for this value can be exponentially close to the true value when with respect to these steps L. And if we have that, we can still have the approximation L to sampling of the computation. And I list out a few results. Like this is a most canonical multi-spin system, which is a graph coloring problem. And here actually we're showing that if the number of coloring is larger than this quantity, where delta is the maximum degree of the graph, then we have a FPTAS to count the number of coloring. And if for the general multi-spin system, we don't really have a classification, but we have some sufficient condition. If this some definition I cannot detail, if we have these conditions, then we have a FPTAS to compute the these are all have exponential improvement results. And here these two are multi-spin system, and now I introduce two multi-party system. So here's a combinatorial problem which counting the edge cover of a graph. So edge cover of a graph is a set of edges such that every vertex has at least one edge on it. So this subset is a edge cover of the graph. So for that, we want to count the number of edge cover. Previously, there's only FP-RAS, which is a randomized algorithm known for the 3 regular graph based on the sampling method, which is called MCMC. And recently, with Lin and Liu, we actually showing that using the correlation decay technique, we can give FPTAS for general graph without any degree of question. Okay. Yeah.
And you started a new topic at the very end. Question?
So the algorithm uses this marginal probability calculation, but does it imply that the correlation, exponential correlation decay implies that also the message passing within propagation algorithm will work?
Yeah, good question. Actually, you should modify the original propagation algorithm a bit, then it really implies that's the correct. Yeah, but you have to modify that a bit because for the original message passing algorithms, they actually do all the calculation one time. So basically, for one run on the recursion, you actually compute the marginal probability for all the vertices. That cannot be done because we need to transform this to a self-ordering working tree. So basically, you need to compute each individual marginal probability by a separate run of the recursion.
So does it explain machine learning algorithms, why they work in some settings?
Yeah, I think so. Yeah.
You can study the same correlation.
Yes, exactly.
Can you show this contraction slide, the contraction, where you discuss the contraction?
Yeah.
So, isn't it equivalent to, I don't see how you can modify by phi to make it contracted. Doesn't it mean that the eigenvalues are of norm strictly less than 1?
Yeah.
That's what it means, right? The
It depends on what norm you choose, but yeah, in some certain norm, yeah.
No, but eigenvalues have only one norm. There are not choices. It's a complex number. So you take the J of X, that's the Jacobian matrix.
Yes.
And you take the eigenvalues of that. And that should be strictly, the eigenvalues should be norm less than strictly 1. Isn't it the condition for contraction?
Yeah.
He wants it sort of twisted.
Yeah, but
So what's it?
by phi reversed, you are not changing the eigenvalue.
No, it changes that.
The Jacobian phi is evaluated at different points.
Yeah. This is phi of the F. Yeah, component. Yeah, it changes. Yeah.
That's what I was thinking.
Oh, okay. That's right. So you are, you're right. So you are composing at different points. Right?
Yes, exactly.
Okay, so that can bend. So
So I think it looks like a very natural mathematical problem. Yeah.
I mean, there is a standard.
Contaction, it sounds like an interesting.
Yeah.
There is a standard, right?
Right.
Lyapunov stability theory on contractions. I mean, there is a well-developed machinery in that.
Oh, really? That's good. Yeah. I think something related to this dynamic system or something like that. Yeah. But I don't really find some tool which can be used. Yeah, I think this is a very natural mathematical problem.
But it's not going to be true for all f. That's
Sure. I want characterize work. Yeah. Some f is true. Some
Nice sufficient condition.
Yeah. Some exactly. It cannot be true for any f. That's.
Let's close the session here.
Thanks.
2 o'clock sharp.
So I have all the right.